like Chris said, and more specifically, like to walk through some of the thinking process in laying out and developing a drainage design on a roadway project and some of the considerations to meet the constraints that you have with both the roadway and the drainage side of things. I'm not really going to get into specifics on sizing a system or some of the calculations we do, although I'll touch on that a bit. And I'm also not going to get on, I think this would be another good one for maybe tomorrow, or Jennifer and William Ricky, is to do a how-to on some of the tools we have to accomplish this in open roads. Some objectives for today. I'd like to start out by, in the next slide, showing you what I mean by drainage outfall, because I'll be throwing that term around loosely. It's really important when you're approaching a drainage design to know what your outfall is, and that could be on a large or a small scale level. And so we always have to be considering that no matter what we're doing. Also, I just want to give everyone, I hope this gives everyone kind of a good overview and understanding of how to start to approach developing your drainage designs. And this could be whether you're just doing a piece of an intersection or whether you're doing a whole schematic for a 10-mile long project. In that case, you're really just doing this process multiple times and breaking it out into bite-sized chunks so you can handle it. And finally, I'd like to introduce a calculation spreadsheet that Texas Pelicans have been working on, Delise and I primarily, and that will help with, I think it'll help you on some of, if you ever need to do some basic ditch calculations and you've generated a ditch profile. The spreadsheet automates a lot of it, so I hope it will help save some of y'all time. So the concept of drainage outfall really needs to be the starting point when you approach your design. You need to identify where your outfall is going to be. And so I found this picture. I think it's helpful. Let me see if I can get the pointer up. So if I'm designing this storm drain system for this roadway, then my outfall is going to be the stream right here. And I need to start with what kind of depth, what kind of elevation do I have, and work my system back from there. If I'm doing something for this house, it might be this storm drain itself is the outfall I'm considering. So that's what I mean when I throw out the term drainage outfall, is where we're taking the water to and where we have to design up from to the highest point in our watershed area. So the outfall being the lowest point, and then we have to take all the water from the highest point in our watershed to that point. So I hope you can make out what this sketch is. I put this together to try to illustrate some of the complexity of roadway drainage and to help start thinking through how we approach developing our drainage design. So I like to think about, if I was a drop of water, where would I go? And you really just have to take segment by segment of whatever you're designing and really think through in detail, cross-reference a lot of the roadway sheets, bridge sheets, retaining wall sheets, look through cross sections, but starting with where am I trying to take this water to? So this could be what this picture is supposed to be, if you can read it, is a bridge at an intersection where you got some frontage road and there's a cross culvert going underneath and going to a main creek. So if you consider the water coming off this main lanes, it's going to have to go down some riprap and go into this down the flume. And then we might consider that, hey, we don't want the water just sheet flowing across the roadway because it's going to be a little bit concentrated. So we need to depress it a little more, put an inlet there, and drain under a pipe. So we need to have enough cover under the roadway to put a pipe and go into this ditch. And then, of course, we have the cross culvert sizing for a major structure like this. So if a drop of water falls right here, it's going to take a path like that. And the one right there. So I think it helps to kind of show some typical scenarios that we have in roadway drainage and what you might be faced with. So the design approach, I kind of took a step back because I've been doing drainage design for umpteen years now, and it kind of comes second nature to me. But I think what I do when I see a drainage problem is first I identify what I'm trying to design. I'm calling that zoom in. So I want to understand the scope of work that I have to actually manage and develop a design for. After that, we need to zoom way out and look at things like the overall drainage area maps, if they've been developed, or the floodplain maps, and get a big picture of where the water is supposed to go. Because as drainage designers, we always want to make sure that we're not sending any more water to properties and streams than was there in existing conditions. So we're not flooding anybody. From there, once I've gotten some of those answers, we slowly zoom back in. And as we zoom back in, we want to identify the outfall, identify what elevation we have, how much depth we have, and then start to develop a drainage profile that manages the constraints that we are tied to with our right-of-way, roadway, and storm drain design. I have this last point in there. I see this quite a bit with new engineers. They'll start just showing me a cross section and think that we can figure out everything from there. The cross sections are very important, but we really should be starting, if you don't have that understanding yet of where the water's going, if there's anything draining towards you that you need to pick up and take further along, you can't start at the cross section view. So I've picked this piece of a project. We just recently, we're almost at signed sealed plans level on this project. This is State Loop 335 in Amarillo and approaching the 1061 intersection right here. And more specifically, we're going to be looking at the drainage in this, which is this area here, which is a ditch corridor. And then we got a ramp here and the main lanes on this side, northbound main lanes on this side, and also the drainage between the northbound main lanes and the northbound frontage road. So in here. So as I zoom way out, I'm going to look at things like the floodplain map, the offsite drainage area maps, 10 risk contours, USGS quad maps, Google Earth Street View, and if you haven't done it already, probably a site visit is very helpful to get a big picture of what's going on. So this is the floodplain map for this area that we're looking at and walking through. Looking at this, and really I'd look at the floodplain map before it. This in itself wouldn't necessarily show you a big picture, but you'll just have to take my word that you can tell that the water is likely to in some way make it to this West Amarillo Creek tributary here. So we're dealing with this area in here. So I get a high level view of that looking at the floodplain map. Still zoomed out, but a little bit less so. We're looking at the overall drainage area map. From there, we're looking at 10 risk contours shown on there, and we can see that it's showing the same story as the floodplain map, and the water is generally draining toward the north, toward that West Amarillo Creek tributary. I'm going to slowly start zooming back in now. And here we might look at our actual contour maps from survey, as well as our roadway profile that shows the cross drainage structures and internal drainage area maps, roadway cross sections. I want to emphasize it's important when we're developing the roadway profile to include the crossing structures on it at the beginning, and the surveyed ones, we probably have to replace some of them, but just to get an idea of the elevations of those so that we don't end up making a mistake on our profile, as well as the water surface elevations once they've been calculated. So zooming back in, we can see, we know the water's coming this way. We can see there's a ditch on this side road that's really taking the water away. So this becomes the outfall that we identify. And there it is in plan view, and in the roadway profile, we see the crossing shown in profile view, so we know its approximate elevation. So now we're ready to start to develop our drainage profile and manage the constraints that we're given. And from what we know now, we know the water's going this way. There was another crossing here, I didn't mention that, but this will be taking the water that's upstream of us. So we are at pretty much the most upstream point in this area that's going to this outfall. So if we were to take a guess at what the profile would be, we might lay out something like this. Starting here and then need to get it to that culvert or to the ditch near that culvert. So now looking at what that is going to look like in our cross-section view for this area and this area, because those are the two, that's this ditch and this ditch. We get something like this, which from a drainage perspective, that would, if the roadway came and said, hey, we want to put 30-foot retaining walls right next to our road, and this is just what we want to do, from my perspective, this works. I know I'd get a call from Gary in a couple of hours, but I have no problem with it. But we know this isn't the most feasible design. So now that we see what it looks like in cross section, we can start managing these constraints and adjusting our profile to make something more workable. So we do this piece by piece and work it through the corridor because it needs to work everywhere. But generally, you get it to work in one area and you follow the roadway profile or what the land's doing, and you can get it to work for a good stretch. And then you look at another area. So I'm going to raise the red profile, which is, I'm going to raise this ditch's profile first. And you see that now we have a nice reasonable side slopes, and this is also ideal in the drainage world. We got a nice flat bottom ditch that's going to have plenty of capacity. We almost never have to worry about a ditch like this not having enough capacity unless we have some major stream flowing into it. We're going to do the same thing for this ditch over here. So we've raised this one up from down here to up here. Now we have a large elevation difference between these northbound frontage road and this main lanes. So we do have pretty steep slopes, and this area and design ended up needing to be concrete riprap, but it works, and we got some guard fence to protect drivers, and it drains to the outlet that we want it to. So at this point, we could look back and say we've managed the constraints for drainage up until this point. Now, as we look further, just evaluating the plan view, we know that there is a bridge going over 1061. These main lanes go over 1061. So we know that getting closer to 1061, we can start thinking, we know the frontage roads are going to be much lower than the main lanes. So that's going to be a challenge. We also see that we lose this space between the main lanes on the southbound side and the main lanes on the northbound side. So we're not going to be able to carry this nice wide ditch down in this area. So we're going to move forward, look at a section like this. If I were to take the profile that we have here now, again, it would look like this in cross-section view, which is not very practical for design again. So on starting with this side, we may consider that we need to flatten out this profile and bring it underground in a storm sewer system. So when you do that, you also need to consider how deep your drainage structures require you to be, but it will allow us to pull that red profile up a little bit. We could capture the water in something like a safety in treatment and then put some inlets along the main lanes, because now we're concerned with ponding because we are draining water along the barrier here, the rail. So we have to check our ponding, and this is what we ended up doing, is putting a series of inlets here. And now our outfall is actually over here, this ditch that we were draining to. So we know these frontage roads are low. So at the end, we need to drop the system and come out to that ditch. So our drainage profile, we've worked this whole side now, and it's come down here. We can keep it reasonably shallow through this area, so we're not having to construct a deep storm drain system. But then we're going to have to drop the system to get across the frontage road. So then we drop it and go out to the ditch. So this is our drainage profile for that side. Now, if we come over to this side, this almost looks workable with the concrete riprap. It's very steep. And in fact, we did have a steep concrete riprap ditch up until a point here. At some point, there's going to be so much elevation difference that this might not work. So we're going to zoom ahead. And at that point, what we need to do is bring the system underground and implement a retaining wall. And so this has ended up being what we did with this design. So the retaining wall will capture the water coming off the main lanes, and this is sloped somewhere where it will be captured in an inlet. And then this ditch will end, and we'll again pick it up in a SET. And because we need to be a little deeper to cross the road here, we put a manhole in and then drop the pipe a little bit, and then drained out to a pond that we have here that also drains to this outfall. So I hope that makes sense and you can kind of follow and follow the process and apply it to your projects. So this is showing off a little bit of William Rickey's open roads corridor work that for this area we were looking at. So this is the southbound side where we captured the water in SET, and this is the series of inlets that we show, and dropping it, going under the frontage road and outfalling into a ditch. And then we have a concrete riprap line ditch on this side that's draining as far as we can, and then being captured in a SET, connecting to a manhole, dropping, going under the frontage road into the pond. So one of the things we need to think about in our constraints, one of the key things is really cover, I say here. Whenever you introduce a driveway, you're going to have to check that you actually have the depth in your ditch to fit a pipe underneath it. If you don't, there's workarounds where we put an inlet and bring it into a storm drain system, but it's best that we just try to use the driveway culverts when we can. Again, and it's also another constraint is the slopes. It's desirable to keep velocities between 3 and 6 feet per second. Sometimes, like these projects we get in Amarillo, it's so flat out there that we have to sacrifice some of these requirements just to make it drain positively, and we deal with velocities less than that. Any velocities steeper than that will likely, or higher than that, will likely need some kind of channel lining to protect against erosion. Another design tip I have for you is to really know your drainage structures and the minimum depths that they require. Because if you're in a flat area and you introduce some type of inlet, you need a certain amount of cover before you can reach your top of pipe. So that automatically drops your profile a certain depth, probably 4 or 5 feet deep. Finally, I'm going to go through some quick ditch calculations. I think whether you're a roadway engineer or a drainage engineer, we should all be able to do basic Manning's equation ditch capacity checks. And that's really all it is for working with ditches. It's just basic Manning's equation. So I don't expect you to actually read all this here, but you know where to find Manning's equation if you need it. The TxDOT hydraulic design manual has some Manning's in values, which is basically a roughness coefficient that contributes to how much capacity a channel section will have. The ones I keep in my head for roadway projects, if I'm using a well-maintained grass ditch or somewhat well-maintained, I usually use 0.03, 0.04, and then for concrete lined, I use 0.013. Another important consideration is your shear stress calculations. That determines whether you need additional lining. So if we have really high velocities and more shear stress, there's a potential for needing to concrete line the ditch or put some kind of erosion control blanket, permanent erosion control blanket down to help reduce erosion. And the TxDOT HDM has a list of different materials and channel linings and what their permissible shear stress levels are. You're basically going to make sure that the actual shear stress when you do your ditch calculations is less than the permissible shear stress when you're doing your design. So this is just a walkthrough of what you need to know to execute some Manning's equation calculations. So if I had a basic trapezoidal ditch channel section, and this is the maximum depth here, and you got your bottom width, your side slopes. From all that information, you can calculate your wetted perimeter, which is the length along this section that is the dry length along the section that is underwater. And then your cross-sectional area. And the only other, and then the Manning's roughness, which we showed a table from the TxDOT hydraulic design manual that gave a list of some Manning's roughness coefficients. The only other component in the calculation is your slope, which can be obtained from, this is a profile showing our ditch profile slopes. I don't want to use this to kind of as a precursor to showing the spreadsheet that we have that will help with ditch calculations. So if you have some kind of profile, and it doesn't have to be a geopack profile, but that's what our spreadsheet is made to work with. The channel section and then your longitudinal slope is what's going to drive your capacity. So if we look at doing ditch calculations along this whole stretch of ditch, it's going to change in each segment of the ditch. What the spreadsheet I'll show you, I'm going to walk you through it real quick. It does is it breaks, if you input a profile, it sets up your calculations to where it does each segment of the ditch for you. So I'm not necessarily saying that we have to do this on every project. Sometimes we can just look at critical areas, but if there's a need for it, this is set up to make your life a little easier. So this is a look at it, and I'm going to walk you through a quick example. I'm going to escape out of the presentation for a second. So say we have this ditch profile here. This is a geopack profile. If you have another format, the spreadsheet will still work. You just need to you just need to have your VPIs and your ditch flow lines. So I'm going to copy this data. I'm going to go ahead and clear out what's in here. We go to the raw data tab, and clearing that out, I'm just going to paste the ditch profile. And then go text to columns, delimit by tab and space. That is data, text to columns. Now, work with me here, Excel. Let's see. Okay, I think I messed something up when I pasted there. Text to columns, delimited, tab and space. Next, finish. Say okay. And I put this in the notes here that just make sure your station data ends up in column C, which it has. Your elevation ends up in column D. So if you have another type of ditch profile, you could just copy those into C and D. And now we have a macro embedded into the spreadsheet. So if you just hit this button, hopefully it'll work now that I'm presenting it to everyone. So what it did was it went through and copied all those ditch VPIs into this inner ditch geometry location. So every station and flow line elevation. And then it gave it a sequence to analyze because you want to analyze from upstream to downstream. So if you have a high point, you actually need to look both ways on the VPI, and it's set up to do that. So it sets up a sequence to look at. The only manual entry you would do is you would enter the geometry as far as your side slopes, bottom width, and the depth that you have. And then it went ahead and pasted that sequence here, and then it uses VLOOKUP to pull up all your ditch geometry in these spreadsheets. So it creates a row for each segment of ditch that you have in your project. And now from here, now that's calculating based on the actual depth that you have available, or based on the maximum depth that you have available geometrically. So if you were to actually know your Qs, you would come in here and adjust your actual ditch depth, which is how deep the water would actually get, until, so say I had 10 CFS there. Right now it's saying my Manning's Q at that actual depth of 1 foot is 52 CFS. So I know it's less than that. I'm gonna say 0.5. I'm just gonna try to get it pretty close. It's not an exact science. And as far as getting the Qs, this isn't an exact science either, because we're not gonna develop drainage areas for every VPI. You're just gonna have to look at your actual drainage area map and make guesstimates on how much flow is in the ditch at that point is what I recommend. So then it gives you your Manning's Q, so I can calculate it. That's pretty close. That's almost close enough. I'll say 0.43, 10.7 CFS. And it gives me my actual velocity, 3.69 feet per second. And then I scroll over here, it gives the maximum shear stress in that calculation. And I can drop down and select a channel lining. And this is less than the maximum. So this is seeding without a soil retention blanket, which is less than the maximum permissible shear stress for that lining. So it says I'm okay. But if I were to change the depth and just make it a lot more flow and a lot faster, so now it says no, change the lining. So then I could do something like rock. Well, maybe that's a little bit much. That's outrageously high flow right there. So let me, that's giving 555 CFS with the section I have. So that's a little bit too much for 12-inch diameter rock. But if we put something more likely to happen, it will tell me that that's okay with that channel lining now. So it's just something we've developed to kind of help work through these scenarios where you need to do those checks. We also have one tab in here if you just need to do a single section capacity check, and you know your bottom width, your depth, your side slopes, your Manning's in. You can do your ditch calculations for that one section. If anyone needs help, actually, when they get to using that spreadsheet, I've stored it here on ProjectWise. Chris, I've stored it in our folder, which says do not use at the moment, but if you want to just go grab it from there, I don't think he'll have a problem with that. Otherwise, I can provide it for you.
Yeah, that'd be a good thing. And we can send a link to wherever that is to everybody.
Perfect. And that's really all I got. If anyone has any questions, be happy to try to answer.
Eric.
Yeah.
Who does the first pass at ditches?
I don't really have a strong opinion on that. But if roadway does it, I want them to be thinking it through like we think it through, and thinking about, don't just allow geometry to automatically go off at a 4-to-1 and think everything's going to be okay. Really make sure we have positive drainage to the outfalls to save us time going through these projects. I think it can be done either way though, whatever makes sense for the project.
Who's all on the Pelican team?
We're not pelicans. That's what Eric tells us. There's prettier water birds than pelicans.
There's some dispute about the name we're coming up with, but it's starting to take some traction.
He's trying to force his way through and assert his authority.
It's all of Texas Drainage. Me, Jonathan,
Yeah.
Samara, Eric, Julius, Tara, Danny, our intern, Ivy, all of us.
10-4.
Anyone got anything else?
I give you your props for attempting.
So, Eric, I'll have a couple of things I'll just mention to the group. One thing is that one of the biggest risks that TxDOT has is adverse impacts to adjacent properties related to flooding. And I know y'all do a lot of work to analyze that and make sure that there aren't any adverse impacts, but that is a very important part of what we do. And so all of this is really important, not to mention even with your talking about the ditch lining and things like that, those can become maintenance problems over the long term. And so if we don't address that in our design, it becomes a problem to TxDOT. So all this is good that you're sharing. But the last thing that I'll say is that we've had these discussions, but I'll continue to repeat it. We're all in this together, and what we don't want to have is we've got to work together, particularly as roadway designers and drainage designers, because as you just demonstrated, all these pieces and parts fit together, and we have different focuses, but we need to take responsibility for the whole project and the whole design as a team. And so it's important. I mean, I really enjoy drainage personally, but I think that good drainage engineers need to know about roadway design, and good roadway designers need to understand drainage design, at least to the point that we can watch each other's back. And if there's an issue that may not be directly related to our responsibilities, we can bring it to the right people's attention. And so this presentation and giving everyone, regardless of their role, an overview of some of the stuff that y'all do, I think is really beneficial. And I think that if we take that attitude as a team, as we work together, that's going to help us to every one of us to be better. So just keep that in mind, and thank you for your time to put this together. I think it's been really good and hopefully helpful, particularly to those that, you know, haven't had as much exposure to the drainage design. So thank you for your presentation.
Yeah, and I didn't really stress it, but on the drainage side, we want to be really, it's really critical, because if we're not identifying and looking through and understanding the roadway and how things are going to tie together, we're the ones that are, drainage is very susceptible to having to, roadway as well, but if something changes late in the game, it's susceptible to really causing us to go over budget and over schedule, because there's so much rework that has to be done. We really need to think these through, so we're not revisiting the culvert modeling multiple times during a project, to where that's one and done at the beginning of the project, and then you kind of build upon your design successfully, if that's the right word, or incrementally as you go further along in the project, but not unbuilding what you've already started.
Thank you.
That's
Anybody else? All right, well, that's all I've got. Thank you, Eric. It was a good presentation. I'm gonna go ahead and stop recording, but this will be